So at this point, we are just coming off of a video in which we introduced the idea of the inverse to the exponential function. And we called it the logarithmic function. And what I want to do in this video is I want to look at some very basics of working with logarithms. In order to do this, we are going to take a second to review some of the basic properties of exponents. So I'm going to write them over here in this box on the left-hand corner. So the first thing I want to remind you of is that if you take a number and you raise it to a power of 1, you just get the number itself. And the other thing I want to start with reminding you is that if you take a number and you raise it to the power 0, you get 1. And I have to put here that this is unless a is equal to 0. But because for our purposes, the bases of exponentials are going to be numbers greater than 1, that's not really something that we have to worry about at this instant. It's something we should be aware of, but it's not something we have to worry about. Beyond these two kind of basic introductory moments, I want to remind you of 3 properties of exponents that we're going to be using intermittently and all the time. If you remember them from like past experiences, feel free to say along with me what the property is. So the first property that I like to look at is the one that takes 2 powers of a and multiplies them together. And what happens is we can consolidate these into a single power of a where the power is the sum of the other 2 powers. So a to the power m times a to the power n is equal to a to the power m plus n. The second property has to do with division. So a to the power m divided by a to the power n can be consolidated into a single power of a where the exponents subtract. And then the last property is if you have a power of a and that's being raised to another power. So what happens in that instance is that the powers multiply. Okay? So I want to get these properties on the page, even if we don't use all of them right now, because these are going to be part of our general conversation in the next few videos, and it's important for us to see them over and over and over again so they become more and more familiar. So the other thing I wanted to say before we dive into all of these examples is I want you to remember this thing that we talked about at the end of the last video. So this is in some sense the most important thing that we're ever going to say about logarithms. Because logarithms are the inverse of exponentials, if you take an exponential relationship, so a to the power b is equal to c, where b is the input and c is the output, you can rewrite that same relationship logarithmically. So here you'll notice b is the output and c is the input. So the input and the output switched places. And any logarithmic expression can be rewritten in exponential form. Any exponential expression can be rewritten in logarithmic form. So that interchangeability is super central to everything we talk about with logs and exponentials. Okay, so with this at our back and with the properties of exponents to help us, let's dive in to these conversations. So these examples are sort of a mishmash. They're not necessarily from homework, although they're going to be very similar to problems in your homework. So I'm going to do them in order, even though some of them may be easier than others. So log base 2 of 8, what is the value of that? Well, what I want to start with is I want to start by labeling in accordance with our red box up at the top here. So here, 2 plays the part of A, 8 plays the part of C, and the unknown is B. Okay? So let's rewrite this in exponential form. In exponential form, we have 2 to the power b. I don't know what b is, so I'm just going to write it as b is equal to 8. In other words, what power of 2 is 8? Now, it so happens that 8 actually is a power of 2, 8 is 2 cubed. So that means that b is 3. And so we can say here, we can use our little eraser maybe. We can erase this little question mark. And we can say log base 2 of 8 is equal to 3. Okay? All right, let's move on to number 2 here, right? So I'm going to do the same thing again. I'm going to label my A, my C, and once again, B is unknown. So you could either continue using the question mark or you could switch to just calling it B. So in exponential form, this relationship or this question, what's log base 4 of 4, is the same as this. So in other words, what power of 4 is 4? And so here I'll direct your attention to our basic properties of exponents over here. And our very, very first property says, if you take a number and you raise it to the first power, you get the number itself. So, oh, well, that means 4 to the first power is 4. And thus B is 1. So if we go back over here with our little eraser, we can say log base 4 of 4 is equal to 1. Okay, let's move on to number 3. So same thing, I'm going to label. So 7 plays the part of A, 1 plays the part of C, and I don't know the value of B, so I'm going to put a little question mark there. But again, in exponential form, asking the question, what is the log base 7 of 1? We are asking what power of 7 is 1. And again, I'll direct you to our properties of exponents here, that if you take any number and you raise it to the power 0, you get 1 unless your base is 0, which we are not concerned with here. So we can say here 7 to the power 0 is 1. So B is 0. Okay, so if we go back over here with our little eraser, we can say that log base 7 of 1 is equal to 0. So what you'll quickly start to see, and maybe it'll take a time or 2 or 12 or however many, is when you have log base a thing of another thing, another way to compute that is to think about it as what power of the base is this number on the inside, right? So kind of like this question we're asking here, what power of 2 is 8? What power of 4 is 4? What power of 7 is 1? Let's look at this next example. So maybe some of you are ready to start skipping steps. And if you are, that's great. You could see if you could try to work ahead, pause the video and see if you get the same thing I get, right? That's the beauty of a video, is you can pause it and you can kind of work on your own and see if it works out. But I'm going to do all of the examples on this page all the way through. So again, using exponential form. So I'm going to write here, in exponential form, asking for the log base 9 of 27 is the same thing as asking what power of 9 is 27. So I'm going to write it. What power of 9 is 27? In this case, this is our first example like this. 9 and 27 are not obviously like very, very, very clearly powers of each other. But notice that 9 and 27, even though they're not like obvious powers of each other that we can immediately see, they're both powers of 3. So we can rewrite this question, 9 to the power b is equal to 27, using all threes. So 9 is 3 squared, and that's being raised to the power b. 27 is 3 cubed. And so in this case, it's handy to use this last property of exponents, which says that if you have a power of a being raised to another power, the powers just multiply. So whatever b is, 3 to the power 2b is equal to 3 cubed. Here, we can actually use the fact that exponential functions are 1-to-1. If two powers of 3 are equal, the only way for that to be true is if the powers are equal. So that means 2b is 3, and b is 3 halves. So we can go back up to the top, erase our little question mark, and log base 9 of 27 is 3 halves. Okay? All right, couple more. Same thing. Again, if you're starting to feel confident, pause the video, work it out on your own, see if you're there. Okay? So we have log base 8 of a quarter is equal to whatever. We're trying to find the value of log base 8 of a quarter. I've labeled my A, my B, and my C. And then I'm going to rewrite this in exponential form. In exponential form, I want to know 8 to what power is 1/4. So in other words, what power of 8 is 1/4? Same thing. You might not look at 1/4 and immediately think of it as a power of 8, but that's where it's handy to notice that 8 and 1/4 are both powers of 2. So that means that we can do something very similar to what we did in the previous example. 8 is 2 cubed. So we have 2 cubed to the power b. And now a quarter. So this is where I'll remind you that 4 is 2 squared. And if you want a reciprocal to happen, you just take a negative exponent. So 1/4 is 2 to the negative second power. And then again, using that third property of exponents, we have 2 to the power 3b is equal to 2 to the power -2. And then if two powers of 2 are equal, that must mean that the powers are equal. So 3b is -2. Divide both sides by 3. So b is -2/3. So if we want to go back here and erase our question mark, we can write that log base 8 of a quarter is -2/3. So one thing that you might be thinking about here is, well, this is all very well and nice when A and C are either powers of each other, like obviously, or at the very least they're both powers of the same number. So it's easy to kind of figure out what B is from there. What if you have something like what we see here in number 6, where you're taking log base 6 of 10? So 6 and 10 are not both powers of any number. There is no number that if you raise it to some nice power, you get 6. And if you raise it to some other nice power, you get 10. Like, you don't have this beautifulness that you had in the previous example. But you do know, like, fundamentally, it's the same question, right? Like, we could still say, this is my A, this is my C, this is my B. So you're still fundamentally asking the same question. So you're still asking, what power of 6 is 10? And even though you don't know exactly what that number is, you can say that 6 to the first power is 6, and 6 squared is 36. 10 is somewhere between 6 and 36. So B has to be a number between 1 and 2. And judging by the fact that 6 is much closer to 10 than 36 is, B is probably a number significantly closer to 1 than it is to 2. So we don't have the capability to answer exactly in terms of like decimal approximations. We can't really give like a super good decimal approximation of what log base 6 of 10 is. But we can say, well, we're asking what power of 6 is 10, and 10 is bigger than the first power of 6, and it's smaller than the second power of 6. So it's somewhere between that first and second power. The examples we just had, number 5 and number 6, show us that you can absolutely have fractional powers. Some of you might even remember working with fractional powers. But even though we can't find the rational number, there isn't a rational number that is the power to which you raise 6 and get 10, we still know enough about what log base 6 of 10 is that we have a general idea of what kind of number we're talking about. So this lays some groundwork on how we evaluate logarithms, how they work, what they are. In our next example, we'll move on to talking about some properties of logarithms and how we can use them to understand logarithms a little bit better. Stay tuned. Bye.